So hi, I'm Jan. I'm a last year PhD student working at HITS with Fabian Scheider and Saskia Hecker. So for most part of my PhD, I've been concerned with the hunt for stellar mergers. And if you remember the introductions from yesterday, I'm a theorist, I'm not an observer. So to hunt for stellar mergers, I computed a grid of binary evolution models with MESA. So I listed some of the settings / ingredients of my grid: solar metallicity. We modeled rotation and tides. Also important, the evolution of both components. And then it's been already a hot topic today. I allowed my models to become non-conservative because of the spin-up of the star, in the same way as Pablo and Kushik described earlier. So I have an example of one of these models here, where you have case A mass transfers on the main sequence. Important here also to understand the models. We model through some of the contact phases. I mean, some, because we only model through the main sequence contact phases. So here you see a system that becomes a contact binary, detaches again, and later becomes a contact binary again. Well, this is going slow. Well, so computing a grid to find stellar mergers not only gives you stellar mergers, it gives you a whole lot of other information. And what I want to do basically today is show you what are some of my results for the mass transfer stability and for the mass transfer efficiency, and where do we find stellar mergers. So the full grid includes 0.8 to 20 solar mass stars. But I'm going to disappoint low mass star people today. I'm going to only be talking about 5 to 20 solar mass stars today. We have the full range of initial mass ratios and the full range of mass transfer cases, meaning the initial separations go from mass transfer on the main sequence all the way to no mass transfer at all. So this and much more was compiled in a paper that was recently published. So you can scan the QR code if you want to get it on your phone, which is not an ideal way of reading a paper anyway, but still. So it's about 6,000 binary models. And I want to dive into the grid immediately itself. So what I'm showing here is a slice of my grid, all the models with an initial primary mass of 10 solar masses. We have the initial mass ratio on the x-axis and the initial separation on the y-axis. You immediately see some groups of the case A systems, the early case B systems. So these are systems where you're off the main sequence as a donor, but you still have a radiative envelope. Late case B systems have convective envelopes, and then everything past for helium ignition is case C for me. So let's look a bit at the evolutionary outcomes of this grid, and let's start with the yellow colored here. These are yellow colored models here. These are all my models that went to runaway or unstable mass transfer. If you want to know what my exact conditions are for that, because I was a bit vocal about it yesterday, they were asking me, and I have a slide for that. And so the thing with these runaway systems is that if you have a kind of fluffy, extended red supergiant donor and a more compact companion, then we expect these systems to become classical common envelopes. So where both cores evolve in the envelope of the donor. And then for these early case B and case A systems, we expect them to turn into contact binaries that will likely merge very quickly because this is an unstable situation. But I promised you stellar mergers. We get a few here, but most of them you're going to find in this case A contact binaries. And these are contact binaries that exist because the accretor, as a result of accretion, starts expanding. And if you keep expanding enough, then you're going to both be filling your Roach loop and you get a contact binary. Now, when do we get a merger? Well, I'm going to show you in a moment. It's not such a straightforward story, but a good indication to say we're going to get a merger is if this contact binary keeps expanding and you get L2 overflow and you lose angular momentum, you get orbital decline and you merge. So I don't know if the contrast is good, but you find them here and here. And so this is kind of a story I just told you. You get a contact binary, it evolves, it evolves, it evolves. You get L2 overflow. I said, well, it depends on the outflow velocity and a whole lot of other things. But for now, for today, let's just assume that when we get L2 overflow, we get a merger, and then you get a transient, which I learned this summer is not luminous and not red, but is a nova that I used to think they were luminous red novae. And after that, you get a merger product. And I'm kind of, overshooting in tomorrow's session now. But these merger products are obviously also interesting. What do they look like? How do they evolve further? For this last question, there is a paper published from Fabian Schneider, Philippe Zadlowski, and Eva Laplace from last week, where they're going to track these merger products up until they explode. And what I'm personally interested in now is, can we distinguish these merger products from genuine single stars, so single stars that evolved or that just evolved in alone, or at least did not merge with another star. And there are several ways to do this. So the first one has been done recently by Menon et al., where they looked at the surface properties of such stars. Another way to do this, and it's also a hot topic, is astroseismology. So there has been a paper from Earl Bellinger where he already did some comparisons, and there is a paper that I'm hoping to submit very soon, where we're going to do more detailed comparisons between merger products and genuine single stars. And one of the big kind of smoking guns is something that Earl also found, is that if you compare this buoyancy travel time for such models, it's basically a measure of how close your frequencies or your periods are spaced. If you compare those, then you can see that there is already quite a big difference there. Okay, so I talked about the mergers, but a contact binary doesn't necessarily need to merge. So what can also happen is that it detaches again. So we were wondering, how do our case A contact binaries look like? And how do they compare with observations? So I've plotted them here, and as you can see, most of my case A contact binaries form at low mass ratios, while most of the observations are at high mass ratios. So a problem. But it doesn't need to be a problem, because if we look at the coloring here, we see that these yellow systems, they're runaway mass transfer, they're unstable, they're very likely to merge very quickly. Then we have the pink ones, L2 overflow, I told you before, they're also very likely going to merge, and then we want to observe them as contact binaries. And now we have the orange systems, where if you look at the hedging now, these are systems where the expansion of the accretor happens because it's out of thermal equilibrium. Now, if the star regains thermal equilibrium, it's very likely to shrink again, and it detaches again, and you don't have a contact binary. Oops. Or in the other case, this expansion just keeps going, and you overflow your L2 point again, and you merge. So most of these systems are either going to merge or detach, while the systems here, they are there because the star expanded on a nuclear timescale accretor star, and there's basically nothing telling it to shrink again, at least until the end of its main sequence. And this is also exactly, these are long-lived contact binaries where we observe contact binaries. So let's quickly go to the, I don't know how much time I have left. 0? My timer says 8 minutes. Okay, yeah, well, very quickly. Stable mass transfer, that's why we're here. We have a whole bunch of models where we have stable mass transfer that doesn't lead to contact. For example, case B and C mass transfer, which is also something I tried to say yesterday. If you look at the donor star alone, you expect unstable mass transfer because you have a big convective envelope, but you have to take the orbital evolution into account. And this is very non-conservative mass transfer, which helps with this. And this is something that Pablo was talking about earlier today. Everything that I hatched in green here are non-conservative systems where the matter that is not being accreted also cannot be pushed away using exactly the same condition that Pablo used, because I got it from his thesis. And so it's kind of scary or interesting. It's basically the whole diagram. So you see a lot of systems that we expect either some matter flowing around in whatever way, and then there is the work of Ruggiero, for example, or there is, here it is, or there must be some better accretion disk physics to explain this. As a kind of a fun thing, we just rerun the whole grid, switching off rotation, so we get fully conservative mass transfer. And I think we can all agree the landscape looks quite different now. So we get a lot of contact binaries and a lot of double core common envelope phases here. And then the last thing I'll show you is we did some population statistics. So with my non-conservative or my original grid to get a lower limit of 12% for stellar mergers of all the interacting systems and about 19 for classical common envelopes. If we now use a fully conservative grid, the numbers almost double. So we get to 23% mergers, 35 classical and double core common envelopes. So it's kind of the two extremes, but the differences are kind of huge, I would say. So I'll leave you then with my summary. I'm sorry for currently going over time. Yeah, thanks.
Thank you so much for that wonderful talk, Jan. We have a question over with Floor.
Yeah, in the plot with the observations overplotted, so what does the probability of the observations mean here?
The probability.
Yeah, there was like a like where you have like, this one. Like the observation points have also some PDF.
Yeah, they have some error bars, if that's what you're asking.
So the y-axis tells me how each observation, how likely.
No, yeah, so that's the confusing part about the plot.
Oh, sorry.
PDF is for my models, and then the mass is just for the yeah.
Sorry, I missed the other axis.
That's why figure captions are important.
I don't know if I've asked already this at some point, but you have the over-contact models, right?
Yes.
So have you done this plot, but with the lifetimes of them to get the actual observable distribution?
We haven't done that yet. This was an idea at one point to do it. And well, we wanted to actually compare it between the fully conservative ones and the non-conservative ones. But I heard from Luc yesterday that apparently modeling over-contact binaries without rotation, without Matthias's work on the tidal deformation might also not be great. So we might have to, but especially, yeah, we could do that for these models, definitely.
Yeah. Well, I guess that's not a reason not to show it.
No. Yeah. That's
it's also important to know it, I think.
Yeah.
So I was about to going to ask you the same question. That was my first question. So you can do this time, weight, and make a direct comparison with the observation.
Yeah.
And my second question is that the merger. Can you tell me? Can you explain us about this buoyancy? You use this buoyancy time scale to distinguish the merger.
Yeah.
Mergers.
So here they are. So the buoyancy travel time is essentially related to the cavity within the star where your G modes can propagate. So well, because the structures of the merger product and the genuine single star will be completely different. A Hertzsprung gap star is basically, in most cases, for low initial masses, fully radiative, while for my merger product, it's actually igniting helium already here on the HRD. So you get a convective core, an intermediate convection zone. So the cavity where your G modes can propagate, they cannot propagate in convective zones, becomes a lot smaller. And this is already influencing the G modes by a lot. It's always, I feel like I had to do a crash course on astroseismology first. I don't know if it makes sense what I'm saying now.
I would like to hear it more later.
Yeah, we can talk about it later. Yeah.
Thanks for a beautiful talk. Really beautiful slides. Also, I really appreciate the advanced pie diagram, which shows how much the field has grown in 10 years. But I wanted to ask about the same plot that Flora asked about, the observations in there.
Yeah.
And I'm sorry if I missed it, but so basically, when you overdrew the box of where the mergers were, there's quite a few systems that actually fall within observed systems that fall within where you expect
Yeah.
mergers to happen. Do you think the observations are wrong, or do you think the theory
Well,
wrong, and you could still have these extreme mass ratio things?
I think you could still have them. I'm not in a position to judge whether observations are good or bad. The thing is, we do, well, according to the models, find models here that are also there because the Jupiter expand on a nuclear timescale, so long-lived models. So we're not saying that there shouldn't be any there. We're more saying that it does make sense according to our models that most of them are on the right side and on the left side.
Do we have any more questions for Jan before we go to discussion groups? Jan, you said you had an extra bonus slide for what you were discussing. I would like to see it.
Yeah, but it is interesting. I think I'm not saying that I'm correct in the way that we define runaway mass transfer, but it's a hard thing to do, right? And so what we tried is we looked at the mass transfer rate, and we kind of saw that if it's doing this kind of a convex behavior, and it doesn't recover, because on the next slide you see that it also does that, but it does recover. So if it does that, and the mass transfer rate also goes above the thermal mass transfer rate, that's already like piece of evidence one. And then the other thing we looked at is if the donor star also keeps expanding beyond its road trip. It's kind of a combination. It relates to what Natasha was showing yesterday, that what this I would call an unstable mass transfer. And this is a case where in the end you also get L2 overflow, where the donor star just keeps growing and growing and kind of engulfs your companion star. So that's the way we tracked runaway mass transfer.